In this video, I want to take a look at comparing two population proportions. We've seen before how working with a single proportion was pretty similar to when we worked with a single population mean. We looked at confidence intervals, we looked at test hypothesis, and we saw how the techniques we're using were very, very similar. I'm going to do the same thing in this lecture. I'm going to talk about the comparison of two proportions, but lean on what we know when we looked at two, or from when we looked at two population means. The way that we compare it, we have our same two techniques. We have our confidence interval technique and we have our test hypothesis technique. Let's start with a confidence interval, and the way that I'm going to do this is very similar to the way I did the single proportion. This is what we know, and again, you guys may not be real familiar with this thing because I didn't ask you to use it. I didn't ask you to go through the math. We relied on the numbers that were generated using this formula by the computer, and we took the numbers off the printout. But the point is there was a formula that generated our two confidence interval endpoints. This would be an appropriate formula if our sample sizes are large. And our large sample sizes, when we're dealing with means, so the left-hand column here is going to be means, the right-hand column will be proportions, but our sample size criteria was that both N1 and N2 were greater than or equal to 30. Now when we're working with proportions, again, there's going to be a formula, and you can look at it. It looks pretty similar. Look, you have the we'll call that the point estimate, or the sample stuff, plus or minus some tabled value times a standard deviation. And you can look at it real closely if you wanted. This would be the standard deviation of the sampling distribution of the point estimate. It's the formula stuff, the theory, the statistics stuff, but eventually you're going to get to two numbers on a printout that I'm going to ask you to interpret. And so there's a formula that the computer is going to use, but we need to make sure we have a large enough sample size. If you look at this top line, it looks like a mess there. But think of it just as n times p and n times q are both greater than or equal to 15. That was our sample size criteria when we looked at a single proportion. And now all I'm saying is we have the same sample size criteria, but we have two samples to consider, sample 1 and sample 2. That's why the subscripts are here. N1P1, M1Q1, M1, oops, didn't say that right. M1P1, M1Q1, N2P2, N2Q2. All have to be greater than or equal to 15. If that's true, then you have a large enough sample that the formula can be used. When the formula can be used, much like we saw when we were working with means, we're going to get to some numbers on a printout. And I'm going to ask you to interpret those numbers. Now, we've had this conversation in the past. We had this conversation when we were comparing two population means. Our goal is to compare these two proportions now. Before it was to compare the two means. We want to know, are the proportions the same? Are they different? Is one bigger than the other? And the thing to think about here is, what would it look like? What would specifically, this is going to be a confidence interval for P1 minus P2. What would the confidence interval look like, or what would the value be? That's a 2. It looks like a Z, but that's a 2. P1 minus P2. If the proportions are the same, what is the difference between them going to be? If the proportion of male students that have a tattoo is exactly the same as the proportion of female students who have a tattoo, if I looked at the difference between those proportions, wouldn't it be 0? And again, we had a similar conversation over here when I was comparing mu1 to mu2. If the means are the same, the difference between them is 0. If the proportions are the same, the difference between them is 0. And so what we do is we look at the confidence, or we look at these numbers here, these guys, but the numbers are less important than the signs. If my interval is entirely positive numbers, what that tells me, if I ask you to question, think about our interpretations of a confidence interval. We talk about a practical interpretation. We are 95% confident that the difference in the proportions falls between these two numbers. The theory and repeated sampling, 95% of the intervals created would contain the true difference in the proportions. And then if I was asked you to a question, a question like, is the difference in proportions equal to 0? If the interval's entirely made up of positive numbers, maybe it goes from 0.2 to 0.7. Doesn't really matter what the positive numbers are. We would say that we are 95% confident that the difference between proportions exceeds 0. And ultimately, we would say we're 95% confident that P1 is bigger than P2. Look back in your notes. Look back in what we've talked about already this semester. When we compared two population means, we have exactly the same kind of logic, the same kind of thought process, but we said mu1 is bigger than mu2. If we have an interval that's entirely negative, flip the sign around. If we have an interval that's entirely negative, I believe the difference between proportions P1 minus P2 is now less than 0. In fact, I'm 95% confident of it. I'm 95% confident that P1 is less than P2, and there's only one other possibility. If you have a negative lower endpoint, those negative numbers in that interval indicate that the first proportion may be less than the second proportion, and then have positive upper endpoint indicating the first proportion might be bigger than the second proportion. And also, if you have this interval, if you have a negative lower endpoint and a positive upper endpoint, guess what number is in the middle? 0. And 0 is the value where you'd say there's a possibility that the proportions are the same. But it's not just 0, so there's a possibility the proportions are different. In other words, I don't know. I'm not sure what's going on. At the 95% confidence level, we cannot detect a difference between P1 and P2. And so the way that we interpret our interval endpoints is exactly the same way we did when we were comparing two means. Very similar technique. The big difference is right here. Another difference that I should mention, if we didn't have large samples right here when we were comparing two means, there was a small sample technique. And the small sample technique worked if and only if the populations we were sampling from were both approximately normal. Now that small sample stuff, again, doesn't work. We had this conversation when we were talking about a single proportion. Small samples and proportions do not mix. So if you don't have large enough samples, you got to go back and take bigger samples. There's no other option. There's no small sample assumption. The populations that we're sampling from cannot be approximately normal. We would have to take larger samples. But the way we interpret the intervals is exactly the same. So our confidence interval checks out pretty nicely to the one when we were comparing two means. How about the test hypothesis? I know you're wondering, so let's go ahead and take a look. The test hypothesis we looked at before, we were comparing means. We wanted to see if mu1 minus mu2. Now, technically, it could be equal to some hypothesized difference, but for all intent and purposes, that hypothesized difference is usually 0 because the null hypothesis here, if you use a 0 value, says that the means are equal. And that's usually what you're interested in. Is there a difference in the means? Is one bigger than the other? Is one smaller? I have the not equal to drawn in here, but we saw how we can do a less than test. We can have a greater than test. The less than, the greater than, saying one of the means is bigger than the other. You do need to be careful with the alternative here. Okay, when you're doing a comparison of means, likewise, when you're doing a comparison of proportions, and I say test to determine if this one is bigger than that one, our tendency, your tendency, will be to say, oh, bigger, bigger. Bigger is a greater than test. And you do need to be a little careful with that, because if I say test to determine if the second one is bigger than the first one, that's actually a less than test. If I ask you to test to determine if the first one is bigger than the second one, that would be a greater than test. So whenever you're comparing means, proportions, and I ask you to do a one-tailed test, you need to pause before you say, oh, we say greater than, let's do a greater than test. Test to see whether I'm asking, is the first one bigger than the second? That is a greater than test. Or is the second one bigger than first? If I'm asking you to compare and determine if the second is bigger than the first, that actually is a less than test. So just something to kind of keep in your mind. You need to be able to identify alternative hypotheses, because the alternative hypothesis is how we generate our printouts. And from our printouts, we get our test statistic. We get our p-value. And now we're back to p-value interpretations, which you getting good at that yet? You should be. We see it all over the place. If p is low, if alpha is greater than the p-value, if p is low, we reject the null hypothesis. If p is high, if alpha is less than or equal to the p-value, we fail to reject. It's our same interpretation. I am not going to change that anywhere in the class. Anywhere that you see me working with p-values, this will always be the case. When p is low, reject the null. And so it's pretty standard stuff. The way that we set it up is pretty much identical. Again, the sample size criteria is here, just what we talked about on the preceding page. N1P1, N1Q1 have to be greater than or equal to 15, N2P2, NQ2, N2, Q2 have to be greater than or equal to 15. All four of them have to be greater than or equal to 15 in order to be considered a large sample. All right, let's take a look at an example and get some experience doing some of this stuff. So let's go to the example. All right, and this example comes from a textbook. May not be the one you're working with, but the role of cell phones in modern life was investigated by a survey. Total of 1,286 cell phone users. This was first when people started using cell phones, when a big push to using cell phones. 1,286 cell phone users were interviewed in a sample, pretty big sample. One of the objectives was to compare male and female cell phone users. For example, 32% of the men. That's a sample proportion, by the way. We're told down here in the bottom, half of the survey is men, half is women. So 600 and what's that, 43? 32% of the 643, that's a sample proportion. Admitted they sometimes don't drive safely while talking or texting on a cell phone, compared to 25% of the women. So the slightly higher sample proportion of men than women. But we're not interested in sample proportions. We're interested in population proportions. Also, 71% of men use their cell phone in an emergency compared to 77% of women, assuming half the cell phone users in the sample were men and half were women. I want to do two things with this, and I just want to use this data to work with confidence intervals and test hypothesis. And so the first one is a confidence interval. Find a 90% confidence interval for the difference between the proportion of men and women who sometimes do not drive safely while talking or texting on a phone. Conduct a test to determine whether the proportion of men and women who use their cell phones in an emergency differ. Let's go to a printout. And so I'm going to need a printout, so let's go ahead and get a printout for the 90% confidence interval. I've already gone and done it. Here it is. Okay, now let's take a look at this printout. Now, depending what software package you use, things are going to be located in different places. So here at the top, I guess let's do this. Up here, I actually told the software what the numbers were. And so I took the sample data and I put it in there. And so the problem actually gave me that number there and that number there. They said 25% of the women, 32% of the men. So sample 1, let's do this, is M, males. Sample 2 is females. Okay, the software I used asked me to it actually does both the confidence interval test and hypothesis on the same page. This information here in this printout is what we look at when we're working with test hypothesis stuff. That's where it's found. And then the information down here is the confidence interval. And you can see that this one says 90% confidence interval. I had to enter that. And here are the endpoints. And you're going to notice this. This is what I'm going to point out to you. The lower endpoint is a positive number. The upper endpoint is a positive number. Notice I'm not even mentioning the numbers. I'm just mentioning the signs attached to those numbers. Now, before I actually do this work, the first step would be asking, is the sample size large enough? And in order to answer that question, I have to take a look at N1, 643 times P1, 32%. I need to take N1 times Q1. What's Q1? Well, if P1 is 32%, 0.32, Q1 is 68%, 0.68. So I take 643 times 32. I take 643 times 0.68. I take 643 times 0.25. That's N2P2. I take 643 times 0.75, which is Q2. All those numbers are greater than or equal to 15. So if I were to take a look, if I was to spell it out for you in the notes, N1, P1, N1, Q1, N2, P2, N2, Q2 are all greater than or equal to 15. This is a large sample, folks. It's a really large sample, actually. And so we have large enough samples to take a look at our confidence interval. So let me go to the next piece here. The 90% confidence interval is given on the printout. But really what I want you to see is it's a positive. All the endpoints, all the values, or I should say both the endpoints, all the values in the confidence interval are positive. What's that mean? It means when I want to do a confidence interval for P1 minus P2, the conclusion I'm going to make is, oops, that's a P2 written in one symbol. That's something I've never done before. That was kind of unique. I'm going to say that difference in proportions is greater than 0 because of those positive numbers. In other words, P1 is greater than P2. I am 90% confident P1 is greater than P2. Now, how do I say that in the words of the problem? This is how I chose here. We are 90% confident that the proportion of all men who sometimes don't drive safely exceeds the proportion of all women who sometimes don't drive safely while talking or texting. That's what this means. The first one is bigger than the second one. We looked at it earlier where we were working with means. Now we're looking at it, we're working with proportions. You know what I haven't talked about yet? I need to? Assumptions. What assumptions are necessary here? And I've spent some time with you talking about assumptions. I'm real big on assumptions. I think they're very important. It's easy to interpret these results on the printouts, but the bigger question is, do you know when to interpret? Do you know when to walk away from the assumptions or from the printout because of the assumptions? The things you need to consider when you look at the printouts to say, hey, should I be interpreting this? First, you got to check the sample size, which I've talked our way through. I didn't actually go and show you the math, but I talked our way through it. And then second, you got to see, are my assumptions met? There's only two assumptions here. When you're working with proportions, the only assumptions you always have random, so we need random samples. I need a random sample of males. I need a random sample of females. And back when this thing actually was done, which was, again, in the early days of cell phones, we need a random sample of cell phone users. You look around today and you think, well, that's everybody. It wasn't back then. You need a random sample of female cell phone users. And so that's one thing. And then the second thing you need here, because we're comparing two of them, this is an independent technique. When we looked at comparing two means, there was an independent technique and there was a dependent technique. Has a couple names: paired difference, matched pairs, dependent samples. When we're working with proportions here, there's only an independent technique. So we need random and independent samples. The assumptions are just based upon how you collect your data. And so both of those, assuming they did their samples correctly here, both of those would be pretty easy to check, and neither of those would be a challenge to making this printout valid. The biggest problem here would be, did we take large enough samples? And again, we checked through that, and the answer was yes. This works. Based on our results, we are 90% confident that the proportion of all men who sometimes don't drive safely exceeds the proportion of all women who sometimes don't drive safely while talking or texting. P1 is bigger than P2, and I'm 90% confident of it. So that's how we do confidence intervals. I should point out that in an older version of this software, this symbol here is how the software wrote not equal to. I believe the newer version of the software can do a not equal to sign. Pretty cheap little package here, cheap, inexpensive. It's got its little quirks. It does a lot of good stuff. I'm actually a big fan of the software. Let me ask you this question. Well, I'll ask it in the context of the next one. Never mind. Hold on. Let's go there. All right, so the second one, we wanted to compare, or we wanted to do a test to determine if the proportion of men, all men, and the proportion of all women who use their cell phone in an emergency differs. Again, we need random and independent samples, except now I'm going to be looking at the test of hypothesis portion. And as I pointed out when we were working with a single proportion, there's a couple different rows of information that are usually given on the printouts. It turns out that the uncorrected row is the one to look at. So I'm just going to scratch that out. If I'm ever to provide you printouts on exams or projects or anything like that, I will take off the information that you don't need to make it a little bit simpler to deal with. So this is the information that you need. But I want you to be able to go through it. I want you to be able to specify the null and the alternative. I want you to specify. It's a test hypothesis. How many times have we said this? In a test hypothesis, you got your four pieces: the test statistic, the p-value, the conclusion. Well, guess what? The test statistic and the p-value are staring you right in the face. They're right here. That's the easy part. You need to be able to specify the test. How do you test if there's to determine if there's a difference? They're not equal to. Could I do a greater than test? Could I do a less than test? Yeah, absolutely. To get this printout, I had to choose the not equal to option. There were three options given to me. There's a little button you push. I chose not equal to because that's what this particular problem asked for. So we got a not equal to test. The test statistic, the p-value, they're not real tough to find. They're sitting right there. Now interpret it. Now be able to write your conclusion. In this particular problem, I used an alpha of 0.02. What conclusion would you make? If I said use an alpha of 0.02, is P low? Looks low. 0.0157, sure, that looks low. Is P low? Yeah, it is. We're going to reject. Now, what are the words? Think about it for a second. Give yourself a little test here. What am I going to say when we reject? How does it start? There is, what's that next word? That next word's crucial when you're making your conclusion, when you're stating the words of the problem. There is when you reject. When we reject, do we like the null? We're assuming the null is true, and now we're saying reject it. So which one do we like? We like the alternative. When you reject the null, you like the alternative. There is sufficient evidence to say the alternative is true. There is sufficient evidence to indicate that there is a difference in the proportion of males and females that use their cell phone in an emergency. There is sufficient evidence to indicate that the part after the that is whatever the alternative says. And here when you have the not equal to, there is a difference in the proportion. And probably a word I could have put in there, there's a proportion of all males and all females. There's a difference in the proportion of all males and all females that use their cell phone in an emergency. We're taking the sample data and we're making statements about populations. There is a difference in the population proportions. Now, a couple things I want you to think through. Okay, hopefully that makes sense to you. And that's kind of the test hypothesis. Again, we need random and independent samples. Again, we would need to check the sample size. I would have to take N1 times P1, so 643 times 0.71, 643 times the opposite of that, the 29%, the Q1, 643 times the 77%, 643 times the 23%, N1 P1, N1 Q1, N2 P2, N2 Q2 all have to be greater than or equal to 15. They're all easily greater than that, large sample. We have random and independent samples, so the same discussion from the first part of this problem. But here's a couple other things I want you to think about. First, suppose someone came along and said, oh, not equal to, and again, that's a weird way that this version of the software used to do it. Not equal to test, I really wanted you to do a less than test. I wanted a test to see if the proportion of men was less than the proportion of women. I can't believe I gave you this printout. Darn it all. Sorry about that. If they did that, if someone gave you the two-tailed printout here and they asked you for the lower-tailed test, what would you do to this p-value? How do you go from a two-tailed p-value to a one-tailed p-value? We don't have a need for it yet. There's not a need, because if I wanted to do a less than test, I can just go back and recreate a new printout. But there's coming a time, it's not too far away, where we're going to have to be able to change p-values on the fly, be able to use what you see on the printout and get what you want. To go from a two-tailed to a one-tailed, we would actually take this number and divide it in half. That's how you get the one-tailed p-value. The other thing I want to look at here is, I did the confidence interval in the last question, but let's take a look at this, because this one, the last one, I had two positive numbers. Here I have a negative lower endpoint and a negative upper endpoint. How would you interpret this 90% confidence interval? What would you say? Hopefully you're sitting there thinking about it and you're saying, I am 90% confident that the first proportion is less than the second proportion. P1 is less than P2. That's how you interpret an interval that's made up of entirely negative numbers. The numbers themselves will tell you how much. I am 90% confident that the proportion of all males who use their cell phone in an emergency, it's anywhere from 9.9 to 1.9. So between 1.9 to 9.9% less than the proportion of all females who use their cell phone. The numbers tell you how much less, or if it was positive, how much greater. But it's the signs that tell you whether you can say there's a difference or not. And so what we're looking at in this video is comparing two proportions. Same two techniques, confidence intervals and test the hypothesis. You need to be able to work through both. With a confidence interval, you need to be able to get your endpoints and make an interpretation. For a test hypothesis, you got to do our four-step dance. You got to be able to identify the test, find the test statistic and the p-value on the printout, and be able to make a conclusion. And for both of them, you need to know the sample size, or be able to check the sample size criteria, and be able to state the assumptions that are necessary. Those are the different tasks. Those are the different things you need to think about when you're looking at some problems. Now, I'd recommend you go and practice. Take a look at some homework problems, because you know that you're going to see this again. Probably in project form, probably on exams. So take a look at it, get real good at it, and if you have questions, you know how to ask them. So long.